because because this series equal to A plus this series. Okay, so that we can write instead of this A plus this sigma, A omitted by this A minus A, and this omitted. Also similarly we have EA minus A multiplied by EA plus this series the identity element. So this element must be the inverse of this element. So EA plus AN and from 1 up to the infinity equal to the inverse of this element. It is very trivial because this element multiplied by this equal to identity. Okay, so that these two are inverse and this element is invertible, so this is an invertible element. Okay, and we prove this statement by these properties. This element is an invertible element in A. Please note that the inverse of all elements are unique. Okay, please note that. The inverse of any element in this set is unique. So if A belongs to inverse A and AB equal to BA equal to identity, this B is the inverse of A. This is very important nodes. Okay, this is very important. Node. Okay, and another statement to the set of all elements in A such that this norm is less than or equal 1 is a subset of the set of all invertible elements in A, or any element of A with this property is invertible. If B belongs to A and have this property, then B is invertible. Okay, for the proof of this, let we have this property. EA minus B be less than 1, then this limit is less than 1. This limit is less than or equal EA minus B, and this is less than 1. This shows that by the part 1, since the norm of this element is less than 1, consider this as A in our Banach algebra. EA minus this element, EA minus A, okay? EA minus B or B must be invertible. And this proves this statement. 3. This set is an offset of A. For the proof of this statement, let's A be an invertible element of A. Then for all B in A with this property welcome dear students, welcome, ahlan wa sahlan. For all, let me remember we are proving this theorem in any unit album of algebras. We have these properties. I prove this and this for any A in A with these properties. A minus A is invertible, and this set is a subset of invertible elements. Now we want to prove this statement. The set of all invertible elements in A is an open subset of A. Okay? Let A belong to this set. Then for all B with this property, the norm of B be less than this positive number. We know that this is a positive number. Okay? Please note that if A belong to this set, then the multiplication of these two elements equal to EA, so that this A is non-zero. And so that this and its inverse, all of this must be non-zero, so that this is a positive real numbers. Okay? And this is an easy note. Okay? This P is less than this. We have for any B with this property, we have the norm of A minus 1B is less than or equal the norm of A minus 1, then the norm of P. And this is less than 1 with this property, because this is less than, let me write more complete. Okay? This is less than 1. So that by part 1 EA minus this element is invertible. Please note that in part 1 we proved that for any A with this property, this element must be invertible. So that by this inequality, if the norm of A be less than 1, then this limit is less than 1. So that this element is invertible too. Okay? So that since the norm of this element is less than 1, EA minus this element must be invertible by part A. Therefore, A minus B or this element A multiplied by EA minus A minus 1B. These two are equal, okay? Must be invertible. Because this is an invertible element and this is an invertible element. We say that if A and B are invertible, then AB must be invertible. If A and B are invertible, then this multiplication is invertible, and we have the inverse of AB equal to the inverse of B multiplied by the inverse of A. Okay? So that this multiplication must be invertible. Therefore, we have these properties. If B belong to A and we have this property, then we see that A minus B is an element of this set, or equivalently A is an element of okay, A minus B is an element of this element, so that be an element of A minus this set. Okay. Or equivalently, B belong to A with this property equal to B belong to this neighborhood of by this radius. Okay, B belong to these balls because the distance of B and 0 is less than this radius. This is a positive real number. We see that B belong to this set. And this shows that and we know that this shows that this bond is a subset of this set, and this is a subset of the inverse element of A. Or let me write this. This shows that A plus this bond by this radius, okay, is less than the invertible element of A. And this is an open set. This is an open set. This is an open set containing A, so that A is an element in the interior of this set, and so that the interior of this in the are equal to the interior of this set, so that this is an open set. This is an open set. We know that a set B, for example, is let me remember that in any topological space such as X, if A be a subset of X and A belong to X, we say that A is an interior point of A. This is the set of all interior point of A. If and only if there exists a radius such that this ball is a subset of A, and we remember that this the ball by the radius epsilon and center A. Okay. Let me consider norm space, not topological space. Okay. In a spatial case. Norm space. Norm space and metric spaces are a spatial case of topological spaces of any normed space X with this norm. Okay. And also we know that A is open if and only if AO equal to A, and this is holds if and only if A be a subset of AO, because we know that AO is a subset of A always. Okay. Okay. So that in this statement we see that for any element in this set we have a neighborhood of A such as this, such that this is a subset of this set, so that this A must be an interior point, and any element of in A is in interior, and these two are equal. And also we have these properties that for the map A from this set to itself is continuous. And this is this statement. Okay, this statement. This holds because if A belongs to this set, and this node X is an element which its norm be less than this. Again, then we see that this element is less than or equal these two norms, and this is less than by this property. So by 1 again, this series must be converged in A. Okay. Also, the inverse of this is an element of this set, and the inverse of this element equal to the inverse of A plus the inverse of A multiplied by this. Okay, because if we consider this multiplication, A minus X multiplied by the inverse of A plus the inverse of A multiplied by this summation, it is equal to, we must multiply A by this equal to EA, A multiplied by this equal to this series, okay, X multiplied by this equal to minus X multiplied by the inverse of A, and finally minus X A minus 1 multiplied by this series. Okay, but this is equal to the identity element of A. Because if we come, if we see these two elements, this equal to minus this summation. It is trivial. Because this equal to this summation. Okay. And from 2 up to the infinity. Okay. This is equal to the summation from 2 and n equal to 1 equal to this, so that this equal to this minus. So this omitted by this, and we have only EA. And this shows that this is the inverse of this element. Okay, it shows that this is the inverse of this, must be the inverse of this element. Okay. Okay. This must be the inverse of this, and we prove this equality. Okay. So the norm of these elements a minus x minus the inverse of a equal to the norm of a minus 1 plus a minus 1 multiplied by this summation sorry, this is minus 1, not I. This I is minus 1. Okay. We write instead of this summation a plus this to the power of n, and from 1 up to the infinity, minus the inverse of a, and this is equal to this only. Okay, x a minus 1 to the power of n, and this is less than or equal the norm of this element then the norm of this series. and this is less than or equal the norm of this, then this summation to the power of n to the power of n and from 1 up to the infinity. Or we can write simply all of this to the power of n. And this is equal to this norm multiplied by this fraction. Because you know that for any element such as y, for example, this series from 0 up to the infinity equal to this, and this series and from 1 up to the infinity equal to this. Okay, now this y in our theorem equal to this element. Okay, and this is for this summation. This is our y, and for this we know that for any a and b, in a we have these properties. Okay, now this summation, the norm of this summation equal to this limit. Okay, x n, and this is equal to this limit because norm is continuous in any Banach algebra. Okay, now this is less than by this property. Okay, this summation and this is less than again this limit. Okay, and this is less than this limit. Multiplied by this norm. So we write this limit is less than this, and this less than this summation. Okay, hence the limit of this, if the norm of x tend to 0, equal to the inverse of a, because we know that this is less than this, and if x tend to 0, if the norm of x tend to 0, this tend to 0, because this must be 10 to 0. Okay, so that this 10 to 0, and so this must be converged to the inverse of a, is equal to the limit of y inverse if y tend to a equal to the inverse of a, and this means that this map is continuous. This map is continuous. Dear students, please note that in these equalities we consider a minus x equal to y. Okay, by this we have these equalities, this norm equal to 0 equal to y tend to a. If x tend to 0, y must be 10 to a. Okay, so that these two are equivalent. It is enough in this session, and we will continue in the next session, inshallah. Dear students, do you have any questions? Okay, thank you and goodbye for now. Goodbye.